No.
Yeah,
A testing? Okay.
A testing? Okay.
Just delayed. Don't know the person's you should know how they talk.
Right.
Holy, right?
Yeah, I know. In fact, I also picked this. But I mean, I picked the obvious ones. Right, Neil.
So the only exception is to get a non-linear response.
In fact, there was a particular sociology of science experiment that was conducted. In which I was supposed to distinguish one
Yeah. I think, but so the question I think is, I mean, if you do the kind of stuff that I think.
But what I said was okay.
Now,
I could get
the more of the neutron stuff.
But then I also
it's
put,
not.
I don't
not
know
a
to do all this at all. I know who
in
to do,
equilibrium,
just
yes, it will be
really
in some
read the
sense. But
site,
if you have all these other options,
I could hear you.
then could it be that the temperature change
Okay, but when
is
you
enough
were
to trigger vortex
guessing
some pinning
the-
that does something to
the person
whatever
answering
it
was,
is? Right? I'm just
you
making
must have
things up.
known this
But
person
I
was
mean,
in
I
a
think it
certain
should be
set, it wasn't
quantifiable in
instead of
some
people.
sense.
This
Well,
was
well,
this was
different
among
things
the
you
half a
could
dozen
do.
people
Half a dozen,
who are
okay.
responding.
That's
Yeah,
what I was
so
offering.
in the
Yeah,
referee
it's
manual,
crazy
right.
thing.
I'm not going to be talking about that.
No, but what is the craziest thing you can come up
Oh,
with?
the craziest thing you can come up with,
And
yeah.
you know,
Yeah.
these things better.
Solid quark stars, yeah.
Yeah, or whatever it is, you know. What is the craziest thing you can do to deviate from
Yep.
a barotropic equation state?
Yeah. I don't know.
On the time scale of a few minutes.
So I would think that happens best the same time it happens in our modes. When the bulk is, the
Bulk viscosity.
This bulk viscosity enters because the pressure perturbation happens exactly on the same time scale as the weak interaction.
Weak interactions are
Right,
what's
so,
taken over.
so now I need a mechanism that tunes the bulk viscosity to sit in the uncomfortable place. Or maybe. And I will ruin all the. No, but I think it's the right kind of question. I think we can do better.
What is it you want to ruin? Just.
Everything.
I didn't think you could ruin everything. You could ruin trying to get the.
I mean, I think he wants to kill the.
Trying to see any. You might ruin the matter. Trying to really get out these hard to get out matter effects.
But
But
I think
but-
when you get, before Satya gets too excited about all sorts of universal relations and how you could use them, I think it would be good to have a sort of some kind of quantified ignorance of the physics that we have excluded in this calculation, right? Is there a risk that some of that could come back and bite you or not? How safe is it? That's all.
Yeah.
I think this is one should be able to
magnetic effects and other stuff.
yeah,
Yeah.
or whatever it
Yeah.
is, right?
Yeah.
And just see what are the possibilities.
Yeah, sure.
So what time scale is the interaction stuff that affects
So we do that. Very strong function of temperature. So for cold stars.
But also composition, if you got hydros, it's a completely different
Yeah,
story. Or quarks, right?
Yeah, I'm not entertaining that dimension yet.
No, well,
So what if these are crystalline quark cores?
We'll come back. We'll come back to those interesting discussions tomorrow. I think there'll be plenty of time to discuss these
But
ideas
then-
tomorrow. We
then I
should
think-
now get started. Greg Mendell will tell us. Are you going to read the?
You can read the.
Tell us about continuous gravitational waves from neutron stars.
Okay, thank you. Right, so I'm over here from LIGO Hanford, and I'm going to stay on the theme of gravitational waves, but go off the topic of binary neutron star coalescence. And this is then an overview talk. The purpose here is to tell you about the other way we try to find gravitational waves from neutron stars. We look for continuous gravitational waves. And so everything in this talk really is from other people who have been working on this over the last decade or so. And I'm, though, going to try to go into some of the recent results that have been published. And to start out with, what are continuous gravitational waves? So basically, these are things from just, could be from an isolated neutron star where the signal looks like a periodic wave. Actually, let me find the pointer here. So you're looking at things that look like sines and cosines. This is your basic quadrupole response of the strain in the detector. You've got some kind of phase evolving. The 2 is coming from the fact that we're typically looking at things that are coming out twice the rotation rate of the star, but that doesn't have to be true. But the phase is basically at pretty much a constant frequency, except there's Doppler shifts occurring, changing the frequency slightly, and then there's intrinsic evolution of the source, like it's losing energy, gravitational wave, so the frequency changes slowly, but pretty much it's like a sine or cosine wave. And then there are these parameters in the formula which have to do with the geometry, so forth, and the amplitudes. You have the amplitude of the gravitational waves, the polarization of them. I'll get to this F here in a second. The inclination angle, and initial phase. So those are the parameters that you're maximizing the likelihood over those to get some match filtering. And then you have the antenna pattern. So these F plus and F cross are the antenna pattern or response of the detector to the plus and cross polarization. And with these continuous waves, they persist continuously, so you're looking over long periods of time, so every day the detector rotates around, so these antenna patterns are changing with time in our case. Not like your inspirals, which you're looking at one point in the sky. So you have to track the changing antenna patterns. And it says down here, we're typically looking at these waves that come from like a mountain on the neutron star, and you get waves out at twice the rotation rate in that case. That's typically what I'll be talking about. I'll give a list of other ways you can get them as well, though. And so when we're looking for neutron stars in the sky, we have to also search for sky position and the frequency and the derivatives of the frequency due to the intrinsic evolution of the source. All right, so the way you get this, you need some kind of asymmetry, of course. And so the thing we're usually talking about is how asymmetric is the star. So this is parameterized by what we call the ellipticity, which would be the moment's inertia along the two axes perpendicular to the rotation axis, divided by the moment of inertia around that axis. So we're going to use this term ellipticity a lot. And if you look at it's a triaxial ellipsoid then rotating, you get gravitational waves of this size. This is the strain or amplitude of the gravitational waves, something like 10 to the minus 24, at 1 kiloparsec of distance. So these things have to be close, even to get this big. At a frequency of a kilohertz, so most of the time the frequencies are lower than that, though it's twice the rotation rate, so I guess you can get up above a kilohertz even for the known pulsars. And for ellipticity of 10 to the minus 6, which is what we used to call, what we thought was kind of the maximum you could get in an ordinary neutron star. Maybe it could be a little bigger than that, but this is sort of the maximum. A lot of ellipticities we know are smaller than that, and for this canonical moment of inertia. So this is sort of what we have to be able to detect.
And so may I ask, is epsilon related to Q if I love Q? Or is that a silly question?
This right here, this is what we mean by epsilon in these equations, the ellipticity. So is it related to the quadrupole moment?
Yeah.
Yeah. It is. It's the fraction of the total.
Or no?
Well, maybe I'm not sure exactly which. I mean, there is a relationship there.
No, it's different. Okay, I'm sorry.
Okay, maybe the amount of quadrupole you're seeing on the star is related to how much ellipticity you have. That's producing gravitational waves.
So this is intrinsic, right? This is
Yeah.
not something that was created by a tidal field.
Oh no, you're right. Okay, I didn't. If that's.
Like an isolated thing that's.
This is just a star that's not actually. It's like a cigar shape, but not very cigar shaped. It's 10 to the minus 6. The difference, and if it was a constant density star, that would be the difference in the radii, how big it is in one direction versus the other, in the perpendicular to the rotation axis.
Right, of course. Okay.
Does that make sense? Okay. So ellipticity is the thing we mostly think about, but of course, when we're looking at periodic gravitational waves, there could be other ways to get periodic gravitational waves, and then there'd be other parameters that would produce the amplitude. Even if I say ellipticity, in some cases, we could translate it to what it would mean in terms of other parameters if it wasn't really coming from this case where you got some kind of mountain on the star, or really think of a continental-sized bulge or something on the star. If you don't have that, you could just have a star that's axisymmetric, but you're not rotating around a symmetry axis or a principal axis. So then you're going to have precession. So you have a wobbling star. In that case, the gravitational waves come out not at twice the rotation rate, but the rotation rate plus or minus this precession frequency. And then the last two A's, I'm going to just switch talk to you for a second. You can get like what are called two-stream instabilities, which I didn't know too much about until I prepared for this talk and realized that's exactly the same thing kind of as the Chandrasekhar-Freedom-Schütz instability. And if you, I'll just switch to another talk here real quick. Whoops. And explain what that is. Okay. So here's where you just have any two fluids or two interacting things. Here we're going to speak about the air and the ocean. So this is just a simple example of how this instability occurs. And here I've got a wave. So imagine a wave going from your right to your left, traveling in the ocean. it's going to feel the air pushing against the opposite direction it's trying to go in, so that's going to tend to damp the wave out. Except if you add a current, that's why the wind's blowing on the wave, but now you just have a current in here that is dragging the wave back opposite direction it's trying to travel in. If that current is fast enough, it's going to drag the wave backwards. And so if it's being dragged back that way, it's trying to travel this from your right to your left, but it's being dragged from your left back to the right. So it's going to feel the wind blowing on it in the same direction it's going in. It's just like blowing on your cup of coffee. It's just going to build the wave up. Okay. So that's your basic, I think that's your basic two-stream instability kind of thing that can occur. And
Almost like the CFS.
and so I'm going to say it's the same thing as the Chandrasekhar-Friedmann-Schutz instability. Here, though, you've got a mode that's trying to travel around the star, opposite direction it's being rotated in. So, and if omega is fast enough, it drags the mode backwards. And then the gravitational wave radiation back reaction pushes out in the same direction it's trying to travel in, and then that just creates an instability. So for lots of different kinds of modes, you have to get the star rotating fast enough to do that. But for the R modes, it's always the situation. No matter how slowly the star is rotating, it's always being dragged backwards, and it's always tending to be the back reaction of gravitational waves on those modes always tend to build them up. So gravitational radiation tends to make all rotating stars unstable. It always tries to make the R modes unstable, but of course internal dissipation of the star can counteract that instability, and so we only think it might occur in neutron stars. So switching back to the other talk. Okay, so these last two are, you could have this, like in a superfluid, you have two fluids there, so you have the possibility of the two fluids moving past each other and creating that kind of instability. There has to be some kind of coupling between them, but there probably would be, of course. Or you can have this Chandrasekhar-Friedmann-Schutz instability. And with the R modes, were the ones that attract a lot of attention. In that case, the gravitational waves come out at 4/3 the rotation rate. So basically, if you have another way of seeing the rotation rate of the star, and we detect gravitational waves at some other frequency, we can look and see which one we're seeing based on the relationship between rotation and the gravitational wave frequency. So that's kind of cool. Okay, but mostly if we're looking at known pulsars, so there's a lot of known pulsars where we see the rotation rate from the pulsar frequency. There we often look at twice that frequency to try to find gravitational waves. So often we're looking at the model where it's some kind of mountain or something, or a deformed star. So for example, the Crab pulsar is at 29.7 hertz, so we look at 59.5 hertz to try to find the Crab pulsar. Unfortunately, it's near the 60 hertz power currents, which gets in the data, so it's one of the complications in the US, not in Europe necessarily. Anyway, so what ellipticity, if we turn in terms of ellipticity, what can we expect to try to find? Well, it depends on, if we're looking at mountains on the star or just continental-sized deformations, it depends on the breaking strain of the crust. If these are in the crust, there could be mountains, I guess, in solid cores and other strange things, which I'll briefly mention here. But for the crust, you have this sigma parameter. It parameterized in a typical value of 10 to the minus 2. And people think that the maximum ellipticity was something like 10 to the minus 6 in terms of just a whole number magnitude. 5 times 10 to the minus 7 or 10 to the minus 6. So that used to be considered the maximum you could get in an ordinary neutron star. What I used to think in terms of this was that, though, if you go to hybrid stars, you've got hyperons or some quark matter, maybe it goes to 10 to the minus 5. If you had quark stars, maybe it's 10 to the minus 4. But of course, people can make things, more extreme. I don't know too much about this paper. Like I said, most of these slides this is an overview talk from people from other papers, but it's been reported that you could have a sigma of 10 times bigger here, I guess, and so you get some recent reevaluation says that maybe we should think the maximum is 10 to the minus 5, but these are, whatever it is, these are maximum values. We know for a fact, I'll tell you in a moment, that many neutron stars have ellipticities much less than these maximum values. So even though they could get bigger, we like to see some bigger ones. A lot of stars don't have that. And I'm not sure what people, I'll maybe have a question later, like when we look at planets and things, how big do ellipticities usually get on objects where we can see them compared to what the maximums allowed are? Anyway, so someone here has an ellipticity, some paper says, you could get up to 10 to the minus 1, that'd be great, because then we could, that's 5 orders of magnitude bigger than the gravitational waves we think we're trying to find. Okay, so what's realistic? Well, if you look at the spin down, if you see the frequency of the pulsar and also the frequency derivative of the rotation rate, then because of conservation of energy, you can say if all that energy that it's losing in rotation was going gravitational waves, how big would the gravitational wave amplitude be? And if you know the distance to the pulsar, you can then set a bound on the ellipticities. And we know some have ellipticities that are lower than 10 to the minus 9.
Correct. All sky searches, don't they already rule out the first one?
Well, it depends on distance. Yeah. It rules out that there's none within 10, maybe 10. Well, here it's like, in the galaxy, maybe in our galaxy, maybe you can say there's none in our galaxy.
Well, just because you don't see them doesn't mean it's not possible.
Well, yes, it may be possible, but none of them have the maximum value. But I think that's the point you're saying. We don't see any that have that big, even if it could be
All
true.
sky searches already rule that out in our galaxy.
But this is a maximum. So
Yeah.
you can't rule out anything by not
Yeah,
seeing it.
and in fact, that was one of the points I was going to make. In a sense, if we don't see a big ellipticity, it doesn't rule out you can't have solid quartz stars. It's just none of them are very deformed. They're all, for some reason, smooth.
If you don't ever see them.
Yeah, if we don't see them, or if we detect gravitational waves with a small ellipticity, we can't say we can rule out things.
Just because we don't see neutron stars of 0.9 solar
Yep.
masses doesn't mean it's impossible to create them.
Yeah, but there must be some statistical argument that if you had some distribution, you would eventually see something up near the tail of that distribution. Blah blah blah. So that's a good messy astrophysics thing to figure out. But
How fast would they spin down, though? I mean, if they
yeah, they might not. That's another thing. They have to be fairly young, otherwise they would have stopped spinning. Yep. So good point. The other point I want to make here, though, is if they're all like 10 to the minus 9, we're not going to detect. If they're all that smooth, we're not going to detect gravitational waves with advanced LIGO, probably from rotating neutron stars. Maybe 10 to the minus 7, maybe 10 to the minus 8. I mean, unless it's close enough. But the thing is, I don't think they're closer than 100. I think the closest neutron star is 100 parsecs away or something like that. And we probably isn't. It's not very likely there would be one closer and also had a big ellipticity on it. So it's possible we don't detect anything. That's just one point I want to make. Of course, and we get the most bang for the buck if we detect ellipticity that's bigger than the maximum value for some models. So you can rule those out. Sorry, so we're okay.
Well, the closest known one is about a little over 100 parsecs.
Yes, okay.
But from the number of the galaxy, there must be some within just a few parsecs, right?
There's been an estimate of what is the closest detectable.
Well, maybe not rotating. It has to be rotating fast enough for us in our band too. So there could be some dead neutron stars because there's a billion in the galaxy. Some dead ones closer, but they're all not spinning very fast or doing much anything. Maybe. Yep. Okay, this slide maybe I'll just skip over. This is just reiterating the spin down limit is if you know the frequency and if you know the frequency and the frequency derivative, and if all that energy and rotation was going into gravitational waves, this gives you a limit on what the amplitude of gravitational waves would be, and that's this small number here. Anyway, so I'll skip over that unless there's questions. So what are the difficulties? If we have these periodic gravitational waves, let's just look for periodic gravitational waves in the data. And one of the difficulties is, of course, that the Earth is rotating and we're going around the sun, so there's Doppler effects. And these Doppler effects are, V over C are these sizes here, 10 to the minus 6 and 10 to the minus 4, which is pretty small except for when you coherently, for example, integrate the data over a year, your frequency resolution is 30 nanohertz. And so your signal is spread over 6 million bins or something like that if you did an ordinary FFT. Of course, what we do here is we just look at where the signal should, you just do time domain match filtering right where the signal should be in a single bin. Essentially, you heterodyne down to that signal down and just look at the data in a single bin. For the known pulsars, but we can't do that for all the unknown ones. We're trying to do a complete template search over all those different possible ways you could drip through all those bins. This is just showing the antenna pattern. So this is like the distance out from the origin here is how sensitive the detector is between 0 and 1 in certain directions on the sky for the combination of plus and cross polarizations, which we sample both of those as the detector rotates. And of course, if the system, I'll point out a little bit later, so we always have these Doppler shifts to the motion of the Earth, but if the source we're looking for is also in a binary system itself, then you have the binary parameters of its orbit around a companion that also creates Doppler shifts. And then it's losing energy, so there's going to be a frequency derivative. The frequency is going to change, and over the course of, we're looking at typically a year's worth of data, the frequency can drift through many bins as well, just through the spin down of the source. So we can't just do simple Fourier transforms. You have to search over Doppler shifts, which means you have to search over different sky positions, hundreds of thousands of them at times. But you can then demodulate. You can do demodulate Fourier transforms that track all those Doppler shifts over longer periods of time. And so if you go coherently track all that information, your sensitivity will improve, typically with the square root of how long you can coherently track the signal. Unfortunately, the computational cost goes up with the 6th power of that time, because you got 2 powers from the sky positions, 2 powers from the first derivative, which depends on frequency. You get the frequency goes up with 1 power, the first derivative. The resolution and frequency goes up, so the first derivative also depends on the amount of time you're looking at and just the amount of data you have. Anyways, you get very little improvement in sensitivity for a huge increase in computational cost, so the whole problem is computationally bound. So this restricts then the coherent time we track things. I think it's between around 30 hours, between 1 and 2 days. We coherently match filter all these different templates, and then we just stack those up and average them to improve the sensitivity. And when you're averaging them up incoherently, you tend to improve after that fact by the 4th power of how many things you stacked up and added up. The 1/4 power, I should say here, 1/4 power. Okay, so that's sort of what we end up doing, and the best we can do with that is what's called our Einstein at Home search, which is a screensaver, part of the BOINC infrastructure where you can download and you get some LIGO data on your computer, and it spends time doing 30-hour kind of demodulate FFTs and stacking them up and sending back results to our servers and so forth. We have other searches just run on our smaller clusters that just take 30-minute FFTs of the data, during which time there's not much Doppler shift to worry about, and we just stack those up. And that's for getting quicker results or looking for interesting things to follow up with deeper searches later on. Okay, so one of the things, I just talked about the Doppler shift, so one of the things that's interesting is in the data, one of the things that is another problem is that there are, of course, in our instrument resonances, there's power lines, there's violin modes of the suspensions that are holding the mirrors that they're just trying to oscillate like any wire would, and so on. So there's all these spectral disturbances, which may be at a constant frequency. We're looking at things with changing frequencies, but there's going to be places on the sky where the frequency doesn't change by much. So if you just take, here's our Doppler shift, the velocity of the detector dotted into n dot's a unit vector pointing to the direction of the source. If you take the derivative of that, sorry, was there a question?
Sorry, no.
Oh, okay. Anyway, take the derivative of that, you get the acceleration of the detector dotted into that, and you can get plus something to do with the first derivative. This is the first derivative of the frequency. This is a Taylor expansion here. We get a parameter we call S, and when this S is 0, which depends on which first derivative you're looking at, there are regions of the sky where that's 0. That means you get very little F dot, so the frequency tends to stay constant. So all the stupid things happening in the instrument at a constant frequency tend to mask out the ability to detect there. So in just a few months of data, you'll get a whole circle in the sky where the orbital, basically something that's perpendicular to the acceleration of the Earth around the sun points towards the sun. And so directions that are perpendicular to that direction tend to be hard to see anything in our continuous wave searches. But you always get this problem, I guess, near the ecliptic poles, no matter, even on a year-long worth of data. You still have places on the sky where it's hard to find things. On the other hand, actual signals will have a certain S associated with them. They'll produce a pattern in the sky that's, with even a single detector, you can figure out where they're coming from. And they tend to discriminate. They tend to, by having to track all these Doppler shifts, you tend to get rid of or smear out all the instrument problems, and you can get better sensitivity. And even a single detector possibly sees something. So here's an example of a simulation, semi-coherent search where we're stacking up power of what a signal injected looks like. So there are, of course, this is where this S factor is probably maybe constant across some region of the sky. And so you get aliasing in the sky. You can't find exactly where it is, but you find a region on the sky. But seeing a pattern like that versus instrument lines make a different pattern in the sky or float at different points on the sky. So you can see, if you see something loud against, and this is like a simulation, so I'm not sure what he put in for noise here. I see no noise in this picture. Noise, which you'd always see some bright and dark spots from noise, but if it's above the noise, you saw something like that, you would be able to tell. It looks very different from an instrument artifact looks like.
What is the signal to noise ratio here?
I don't know. I actually tried finding this paper, and I couldn't find this paper.
Does the color code
But
tell you about the strength?
yeah, this is probably what's called power flux. I have some other talks I could show you. But let me put it this way. In searches I've worked on, you could easily see things with an SNR of 7. Okay, against the background, even with all the trials factors. You looked at trillions of templates. Because we're also doing one of these plots for every different little frequency band. So in a quarter hertz band, all the sky positions, you could see something against the sky, and with an SNR of 7, I'm saying. So that's sort of always what we always end up having to go to these higher SNRs, but about like that. Okay, so that's, I guess I'm only going to have a few more minutes. Anyways, I'm now kind of done describing the methods and the ideas, and just talk about some recent results. Of course, we haven't found any gravitational waves yet. You would have heard about that. So here's one of the recent results. This is our known pulsar searcher. Here's where we get the best results. This is just sort of to impress on you how small of a strain we can actually detect with the years worth of data. We are coherently integrating up the data over a whole year. So this is looking at 195 known pulsars where we know the frequency and frequency derivative in the LIGO band where they're spinning fast enough so LIGO can do something with them. And so on this plot here, we've got frequency on the horizontal axis. And this is the strain sensitivity, the amplitude of the gravitational waves, not the strain per root hertz, not the noise spectral density, but the strain. And we've rescaled the noise in the detectors to what this effective strain you can detect is for each of the detectors in different runs here. This is like S5. Actually, you can't see it up there very well, but that's S6 as well. Under this is S6 and S5 and advanced. Then we have something for advanced detectors. All the black triangles pointing down, these are upper limits from the spin down. So in initial LIGO and Virgo, there are only these two above. The Crab and Vela pulsar are the only two that are above the initial LIGO curves. And there, these upper limits now have been pushed down to where the noise curve you would get after doing these year-long integrations. And there we can limit then the Crab is only emitting at most 1% of its energy in gravitational waves, and the Vela at 10% versus, I think the limit was like, the spin down limit was like it could have been emitting up to 90% of the energy it could have been in gravitational waves.
It's low enough that you have, that's basically best in Virgo, right?
Yes, this is a Virgo result.
And Crab sits at your 60 hertz.
Well,
it's
it's
not-
Yeah.
No, I know,
So
but
both
it is.
LIGO and
Yeah.
Virgo contribute to
Yeah.
No, that I
Yeah.
know, but I mean,
Yeah.
I'm just saying
Yeah.
it's almost
Though
inspiring.
it is, but with a 30 nanohertz resolution over a year's worth of time,
no, of course, over a year.
you do get
Yeah.
far enough away. It's still not completely unaffected, but you can get away from the 60 hertz far enough to.
It's funny, really.
Yeah.
Just look at them.
One of these stars down here is the upper limit.
Yeah, it's
Yeah.
inspiring against LIGO.
So all the stars, and I don't know what the color on this legend, the color coding of the different stars. It didn't write down that. But those are this is what LIGO's upper limits are. Only in these two cases do we do better than you get from spin down. With advanced LIGO, there's many more things above, but down here, these low frequencies, it's great. There's going to be many cases where you can get a better upper limit than you can do by spin down. But the ellipticities would have to be, but for these to actually be detectable, they'd have to have very large ellipticities. Large enough that you start to wonder why we didn't detect something already in initial LIGO, or you have to have some story about. Of course, there probably maybe is a very different distribution of ellipticities for the low frequency guys who are maybe younger, but not spinning very fast as versus these recycled guys who are maybe very older and smoother, but spinning faster, so they're easy to detect.
1 year.
This is all using.
Not for that. I mean, that is real data. For advanced
Everything
LIGO,
up here is real.
Advanced LIGO, you're assuming 1 year.
Yes, probably 1 year. Yes. Yep. So there are some. The thing is, in advanced LIGO, there are some millisecond pulsars where they're spinning pretty fast, so their ellipticities don't have to be way above the maximum. And they could still be within the realm of what you might expect ellipticity to be, and they could be above the curve. So here's where people think, well, there's a case where we might detect gravitational waves, and it wouldn't be. You don't have to wave your hand too hard to come up with why that could be true.
Good to see pictures where you ascribe, say, ellipticity of 10 to the minus 8 to all of these guys and see where they show up. But
Yeah, that's an interesting idea.
All those on the left. way.
Yeah, that's right.
Because the curve goes like this.
I think the most likely place, I think from papers I've looked at, the most likely places where we make any detections, and this is again, hoping that there's a few out there with ellipticities near these maximum values that we see, not all 10 to the minus 9 guys, but some 10 to the minus 6 or 7, or we even hope a little bit bigger, then it's above, it's like 600 hertz, somewhere, you're going to do better of 600 hertz and above, and probably can't see anything below too much. Yeah.
Why would these stars have ellipticity? And I mean, just like the Earth, what's the ellipticity of the Earth?
Oh, very large. 140 in a thousand. I mean, it's about 10,000. It's 1,000 mountain Everest is.
Yeah. I mean, one reason, though, why they would have it is magnetic fields are not aligned with the rotation axis, so you've got an asymmetry just from magnetic fields. So if you had big magnetic, unfortunately, I think you need, someone was just saying before, you need big magnetic, you would get some ellipticity just because there's a magnetic field that's not aligned with the rotation axis, but you need big magnetic fields to make big ellipticities. I think they're in the same realm as just what you get from just how big you can build a mountain on a star from the breaking the strain.
This
Yeah.
limit,
Yeah.
upper limit
On the
ellipticity.
Oh, yes.
For a specific source or
Yes. So the next, yes, and thanks. I should point out the numbers over here. Just saying, what's out of all of these stars are the actual upper limits that LIGO has set on these 195 known pulsars, and they were just showing it that fits the noise curve because we just rescaled the noise curve to show.
One of the fastest.
Yes. Yeah.
Is 10 to the minus.
Or it's probably near down here at the bottom of this is where we're most sensitive, is in this noise bucket down here.
It goes like f squared, right? It goes down.
depends on the distance as well.
And this number depends on the distance, but this one doesn't. Anyway, so we can see, the thing is, first of all, we can detect motions, a delta L over L of the detector, 10 to the minus 26. So first of all, if you integrate the data long enough, you can see super small motions of things, way smaller than the size of a proton, not even 1,000 times smaller, but tens of thousands or 100,000 times smaller. So the fact that you can actually detect this, but you're just making the measurement many, many times over the course of the year in some sense. So you're just beating that down by integrating longer, and then this number here is just telling you what the best is, but of course it's not the best compared to what you get from just looking at spin down.
Exactly, that's the point I wanted to make.
Yeah. This is not telling us.
Spin down is
right.
already telling you it's
Yep.
way down.
That's right. That's right. Some of them have. Yeah, that's right. Spin down is telling us there's some way down here. That's right. Yeah. So yeah. Let me just finish the results. So only if LIGO detects, in my opinion, ellipticities that are large, do we learn something. Otherwise, we're just going to learn the same thing we already know from spin down. If we don't, or if we detect nothing, we just, it only rules out that we just couldn't find a nearby neutron star with a large ellipticity. And why is that? Another, I'll just go kind of briefly here, was we've also looked at directions, certain directions of the sky, like the galactic center. So it's just saying you can do a deeper search by just focusing on one direction on the sky. But here's unknown, these are unknown objects. So when we're looking at known things, we got those really small values for h, 10 to the minus 26. When we're looking at unknown things, we're always getting this realm of about 10 to the minus 24. That's our upper limits. We only can see things about like that with initial LIGO. Advanced LIGO, all these numbers will get 10 times smaller, roughly. Another thing that's new is that we've ignored for a long time because it's hard, is looking at sources like this, but where the neutron star is in a binary system. So then you have orbital parameters to search over. It's already going like t to the 6th power, blah, blah. It's impossible almost. So one method that just got published recently, it's just been posted to the archive and it's about to be accepted by PRD, is this thing called 2-spec. You do an FFT. So this is frequent. This is time. This is which FFT we've done. SFTs are just short Fourier transforms that last 30 minutes or less. So this is like which time we're looking at, and this is which frequency, and then go across each frequencies at different times, do another FFT. That's why it's called 2-spec, and then look for some repeated, if there's a repeated pattern up here, you'll see some kind of spike in the second Fourier transform. This is the methods paper by Evan Getz and Keith Riles, and this is the results that have been posted to the archive that are going to be in PRD. Again, because we're having to do a cruder method to include because of rotation, the limits aren't as good. This is kind of the best we can do right now for cases where they're in binary systems, the sources in a binary system. So the summary of the talk is no discoveries yet, of course. We haven't, though, published all the results in all our data from initial LIGO, so we can't say we're not going to detect anything or we're done doing that. We can always hope. And then, of course, when you know we're underdoing this major upgrades, and actually things are, I hope Mike told you on Monday that things are going right now very well, and next year, it'll take us a while to get to design sensitivity, but the thing is we can lock an instrument again, so we'll have some data again next year, unless things change a lot from what they seem right now. And if you look at those, our best cases are the known pulsars. When we know the spin evolution, we can track that much more easily. And so anything we can get, like from the square kilometer array or any other kind of sources, X-ray, anybody else that can tell us where is the pulsar in the sky, what's its frequency derivative, means we can do a much more sensitive search for gravitational waves from that object. And so that's the conclusion of this talk. Yes.
Do you know the best sort of ellipticity from the two-spec searches?
The thing is, it's a case for an unknown object, so it would be a function of. Let me show you, not that exact one. It would be a function of distance. So how far away a source is. So here's the sort of frustrating thing is, here's a plot that shows, trying to show you how sensitivity and distance and ellipticity work. So here are some contours of ellipticity, very large ellipticities going down from 10 to the minus 4 down to 10 to the minus 8. Here's the different frequencies, and here's the frequency derivative of the gravitational waves. And these plots are for some one of our searches. I wish I knew which one. It was probably S5. Yeah, maybe it is S5 because it's pointing to over here. So this is showing up here for ellipticities 10 to the minus 6. You can see out at these highest frequencies out to a kiloparsec. But let's see, here's 100, but that's 1 kiloparsec, but 100 parsecs away. 100 parsecs away, where the nearest pulsar we see is. Down here at these lower frequencies, it has to have very large ellipticity to see anything. So I'm just saying, to get out to 1 kiloparsec, you have to have ellipticities that are as big as that.
About like this, so the nice thing about a thing in a binary is it could be being spun up with accretion, which would make a mountain.
Right.
Be a fast spin.
Yep.
So
And we want.
You lose a couple orders of sensitivity because the search is harder, right?
If we could see that, like in SCO-X1 is one of the ones we've looked at, and actually he's worked on it, so he can maybe tell us about it. But if you could see the pulsar in SCO-X1, then we could track it exactly, and we could get this much better number. But if you have to do the search over orbital parameters and stuff, in fact, I don't know if you want to add anything to that.
Just the basic thing is, the bigger the parameter space, it just becomes very, very quickly impossible to do your optimal search. So you have to make cuts. You do these semi-coherent searches, so you sacrifice sensitivity for computational costs. And that's why you're seeing these wider parameter space searches. They all have strain up limits that are stepping up in orders of magnitude in the wrong direction.
So I guess maybe I'm just asking, how would this particular all-sky thing change if you were trying to do the binary thing also?
Well, that's basically what the two-spec.
The two-spec wasn't all sky thing, but the way you could plot out for those results, you could take any of those upper limit plots and recast them into a plot like this.
Yeah.
And then you can see if they have these ellipticities, they'd have to be this far away to see them based on the sensitivity of that search.
So
And it's always disappointing, like they can't see very far away unless the ellipticities are really big. And even then, you're not seeing outside our galaxy. I hope that answers the question.
Well,
Yeah. Yeah.
Or,
Okay.
I'm just like, how far away could we, if there's going to be some maximally elliptic system, an accreting binary seems like an obvious place to find it.
Yep.
So how
Yep.
far away can we see those? If they're super.
I think you
they're
could
at the
ask
best
Chris, what is the
radius.
ellipticity limit that you were able to get for SCO-X1?
Well, that I was able to get in my PhD, it was like a
Point
couple of
one.
meters high mountain.
Point
3.
Yeah.
But that's gone down maybe an order of magnitude or 2 since then.
Yeah.
But it's still
Binary
it's
is very different.
not going to realistic values.
Yeah. Yeah.
There's another thing that's related to the binaries. There is another indirect EM upper limit you can
Yeah.
from the torque balance.
And there's a slide on that here somewhere. Yep.
So all I was going to say is that for the SCOX1,
If I can find
we
it.
may just about touch the torque balance limit in a certain band because they're not known frequencies. So the limit of
Okay, it must be way past here.
But we may just touch that with the bounce LIGO for SCOX1.
Okay.
The cross-correlated.
Oh, here's the SCOX1.
I thought that reaches better sensitivity.
Yeah, but only slightly. Yeah.
Only slightly? Only by an order of magnitude.
Anyway,
It's the only ones
yep.
that have done the most recent
The
study.
coherent.
Yeah.
Sorry, the cross-correlation search.
The radiometers, stochastic guys.
Yeah.
Yeah.
This is the torque. This is the torque limit for. This is how when you balance the accretion torque with gravitational waves. This is the value you get for the H. Okay.
What has been, what is predicted for SCOX1? Right?
Yeah, this is what's predicted for SCOX1. We haven't beaten that. We don't even.
An order of magnitude and more above that
Yep.
right now.
Yep. And then I guess if we know the distance, I could turn that into ellipticity, but I'm not.
Distance is 2.8 kiloparsecs.
Right. Yep.
Yes, it's kiloparsecs. That's one of the differences.
Yeah.
compared
It's
to-
kiloparsecs away. Yep.
Yeah. So if there is like an invisible binary,
Yeah.
say 10 parsecs, maybe.
They have to be very clever to be invisible.
Yeah.
I mean, we think SCOX1 is so good because we equate the X-ray, the fast X-rays we're getting from it, and assuming we get the similar strain energy.
I think SKA can do more than just give us pulsars. It can also give us timing information, which can just.
Yeah. We want the.
unknown pulsars.
We want the timing of them, and in fact, and also I should say, Einstein at Home is looking at Arecibo data and other, and LAT, the Fermi data, and is discovering pulsars, and trying to look for pulsars that would be good for LIGO that haven't been found before. So.
I think maybe some of the accreting millisecond pulsars can be very useful. There you have a independent information of the spin period and how it changed at different epochs of time.
Like you're talking about like X-ray burst oscillations or something like
no,
that.
not burst oscillations. Some of the accreting neutron stars also show coherent millisecond pulsation like 1808, 1814, 16. All these are accreting millisecond
Yeah.
pulsars.
Yes.
In that case, you have much better idea of which particular spin frequency and the spin wandering of these due to accretion induced torque. So if you use the
Yep.
independent information of some X-ray satellite like RXT
Yep.
or Astrosat or NISAT, which will be coming, use that as your template and extract the.
Yeah, I'm pretty sure we know about that. I'm pretty sure we talked about those things, but.
Aranava is on this. He's
What?
going to be doing that.
Oh, okay, yeah,
For the SCOX1 sort of approach.
right. But I don't. Is there any low mass X-ray binary or any accreting system where we know the actual spin, or we just have some bounds on it?
Screen per second.
There are 15
Oh.
accreting millisecond X-ray pulsar for which we know the spin frequency better than 0.1 microhertz, like precision.
However, if you do the torque balance,
Yep.
Yeah, so
they're not accreting as much as SCOX1.
Okay. So there's a trade-off that they're just not going to be as good a source, but we know the parameters
They
better.
may be closer.
There are-
some trade-offs.
So there are two systems that have been seen in X-ray outburst and in quiescence, for which you have both the spin up estimate during the accretion phase and the spin down
in quiescence.
in quiescence. And that allows you to essentially estimate the magnetic field, and in the best of all worlds, the torque that you get, the theory torque, should combine with the observed X-ray flux and the magnetic field and be consistent with the magnetic field you need for the dipole spin down in quiescence. And there have been papers, there were a couple of years ago papers on one of these systems arguing that these were consistent. It has recently been pointed out that actually the data is not consistent for these systems.
Mhm.
You need the accretion torque to be quite a bit stronger the standard model suggests. So
Yeah.
that just says that
Yeah.
even in the X-ray data, there's the pieces here that we don't understand.
Yes. Oh, there's pieces we don't understand. I think
That's
that's probably true. But I was going to say it's probably also, I think, just looking at the distribution of the spins and so forth, and I think these X-ray burst oscillations that, I mean, gravitational waves could be definitely involved in the spin up and spin down of neutron stars, but they might not be strong enough amplitudes for us to detect with LIGO. So in other words, it could be still very interesting to understand how our modes are occurring in accreting systems and all these other things to understand the astrophysics of what we're observing electromagnetically. But for LIGO, unfortunately, it's not going to. We're going to look for it, of course, because maybe it's not. Maybe it's going to work out, but it's not clear that we can detect them, or we have to work very, very hard, or we have to get that narrowband detector that Daniel Segg says we're not going to get. If we knew the frequency, like we know some of the cases where we know what frequency to look at, we know where to narrowband the detector, then we could actually maybe try to go for it. Yep. Okay. Yep.
A question would be more to Sanjay. How can we use the fact that we have such a lower limit on epsilon to say something about the strain that can be sustained by the crust?
So as people mentioned earlier, you need a mechanism to build a mountain, and then you've got to have what the strain is, right? The maximum strain is, from Chuck's calculation, larger than what people assumed before. But there are other models that can produce large maximum strain. But I think it's very difficult to imagine evolutionary scenario in which you build such a large deformity in the neutron star. These things are born hot, and they cool down rather slowly. So I think just having a solid in the star produce this, I think is difficult to imagine. But a magnetic field being in some crazy configuration, which is topologically maintained, seems more likely.
But it tends to be, the B squared type ellipticity tends to be too weak. So you need to have some funky superconductor version to crank that up to, to get up to interesting levels, I think, for light.
Yeah.
Again. And very
And they just don't, and they're just, I guess they just are so dense, whatever. The evolutionary history, like some planet running into it, does just like disintegrates into dust on the surface. It doesn't produce it. You can't have collisions and glitches tend to smooth things out. I guess glitches probably over time make it smoother and smoother as it spins down rather than worse and worse. Or, I don't know.
The same underlying physics that makes the maximum strain large also makes it very difficult to build mountains, because the simulations, these molecular dynamic simulations, tell you that it's very difficult to sustain any defect. So if you put a defect in, it wants to move away, and those are related by the physics.
But then the accretion, get back to the accretion. So these are in the young one. The accretion is pouring a lot of stuff onto the star all the time. That can't build up a big continent. You can't build a big bulge over time by accretion.
It starts out as a liquid. It starts out as a fluid.
Yeah.
So
there's no shear.
You don't have any shear modulus to
Yeah.
keep it up. And by the time it gets down and becomes a solid, it's doing it in this regime where
in the Oshobersky Bilstead type model, it's thermal asymmetries due to burning under the hotspots, and then composition or thermal gradients, essentially in composition variations. That's where you get the asymmetries from.
Yeah.
And that's again.
Yeah. And these big, like these burst oscillations are thermal nuclear explosions on the surface. These explosions don't produce a big crater or something, or.
it gets filled in pretty quickly.
Okay. Yeah. So neutron stars just abhor having any asymmetry on them. They just can't.
What about a crystalline interior? Can we learn crystalline interior?
Crystalline cores.
Yeah.
Can we learn something? I mean, because they're, this ellipticity is measuring differences in different directions. Then
right. So
because the density is so high, can't you say something about the degree of,
So the crystalline quark phase is a very large shear modulus. And in principle, you could store a large deformation in them. But again, the question is,
Why?
How and why?
Well, if it could be
Part of the reason is
that big number, then
so
10 to the minus
that
4 would be much less than that. So,
So this is just speculation.
But that's all
right now.
speculation, right?
So if I say that you have a system that can produce a large maximum epsilon,
yes.
and you start the solid off with a large deformation that you put in, and you ask how much time it takes for the deformation to just dissipate away, because the crystal doesn't like that in the first place. It takes a short amount of time is what we are learning.
Why the crystal doesn't like it?
Because it's a defect. It has more energy than the perfectly crystalline state.
I'm just thinking about it. If you have a crystalline core, what shape would it have? Would it have an elliptic shape, I guess, if it is rotating?
An oblate spheroid, I guess, or something.
Yeah. So the electricity would just tell me that this ellipse is slightly, asymmetric. Why would that be?
Well, no, but
less-
so you have to be careful now. So the shape you get from rotation will give you nothing in terms of gravitational waves. It's
That's
a
it.
deviation away from
No,
this.
of course, yeah.
So you have to. So I think that the challenge is, so simply put, the summary I think is you have the maximum, which is big. That's nice. You got the minimum, which you can work out from magnetic field tension. That's too small. So forget about that. And in between, you got the ignorance, which depends on evolutionary history, which is difficult. And as Sanjay says now, the arguments seem to point towards it being difficult to sustain mountains for a long time.
Yep.
So if you can come up with a scenario that gives you a mountain, it will disappear through plastic flow pretty quickly. And that's the problem.
Right, and then the other problem is pointed out back here is if you get a big mountain, the thing spins down fast, and then it doesn't stay around long enough, then it's gone before you get a chance to see it.
If I'm thinking about interior, I'm not thinking about a mountain. I'm thinking about.
So you're thinking about some large defect in the solid, right? If it was a perfect solid and you just spun it, you would get nothing.
Yeah, or
Because
you can
that
think
on
of
a
an
large
electrode
solid,
which
it
is
behaves
not
like a fluid.
which is not spinning exactly on its axis, on principal axis.
Yes.
Okay, with a precision 10 to the minus, I don't know, 8. So why would this configuration be obviously not favored, or so?
No, but sorry, if
The
that
interprecession, yeah,
Well,
yeah.
So what you can
No,
say.
but this
Or
is
wobble.
This is still, you're not, there is very little protection because the misplacement is, between the rotation axis and the principal axis would be, 10 to the minus something, 6 or something.
I think the reality is that here, so I think you can put these results in different contexts, the way you kind of did, right? It's very interesting to find that there is a neutron star out there where we know the ellipticity is as small as
10 to the minus.
times 10 to the minus 8.
Yeah.
Right? That tells us something about how perfectly symmetric this object is. And that tells us maybe that this story about the crust, etc., is true, right?
Yeah, so
I mean, I think
I have a general
that is interesting.
question.
Of course, it's a null result, which is negative, but I mean, it's.
Yeah, the fact that some are that smooth tells you maybe that's what they're all. There's a reason why they all get that smooth.
Right. This is essentially the question I was making.
Yeah.
Sanjay. What is it we can learn in terms of nuclear physics about this? And because this idea of a crystalline core is very disturbing in a way, at least for the kind of things my model is fluid. I want to know whether this tells me that is just a crazy idea. Can I use this evidence to say that it's a crazy idea?
No, I think the problem with that is that, just having a crystalline core is not enough to detect continuous gravitational waves from it. You need to have a crystalline core with a very large defect. Just take a crystalline core, which will be spherical on the scale of the lattice spacing, which is, Fermi's, and spin it, it'll behave as if it was a fluid on that length scale. But now you want to put something there that's going to change the isotropy, and that can only be sustained by a solid. Right? So it's not, what we're saying is that in a simulation, you take a big volume and you create a defect in some sub-volume, and you ask how long does it take for the defect to disappear. It's fast compared to any astrophysical timescale. In a regular solid on Earth, if I make a defect, that defect can last for hundreds of years, because the regular solid on Earth is very different from the solids in space.
So how should I think about it? If I
So
make
the
it
solid on the Earth is held by complicated atomic bonds.
right.
So they can be very metastable. The
Mhm.
solid in space doesn't have any atomic structure. It's just got a very uniform fluid of electrons around it. So things move very quickly. There aren't any orbitals that need to move around to get rid of the defect.
So it sounds like it's another argument for looking in the accreting system where you've got something that's constantly maybe driving and keeping the defect there.
But it's harder because of
But-
the orbitals,
yeah.
so the extra parameters. So
Yeah.
you gain that argument,
Yeah,
but you lose
yeah,
in the difficulty.
yeah.
I think the answer, John, is that you should go back and do all your simulations with crystalline cores. That's the answer. Maybe by
I'll just write an
tomorrow.
application for some computing time now.
But it can be explained by a bulk property, right? You don't need to go into very
But,
detail.
but if LIGO tomorrow,
No. Yeah, no.
If it's-
but if LIGO tomorrow finds a big ellipticity, what paper are you going to write tomorrow to explain why it actually did have a big ellipticity?
Yeah, so I think that'll be a problem. I think if there was a big ellipticity found in a
Yeah.
old neutron star.
I mean, that'd be a very interesting result. What we're, you know,
That would be at odds with these simulations.
yeah, what we're hearing is it's not likely, but if that happened, that would be, of course, very interesting.
This would not be our problem because there's enough clever people in astrophysics that would write papers, the same day that would explain this in 100 different ways, and then we can have conferences about it. So that would not be a problem. We might not know the answer, but we're going to have many interesting papers. That's
Yeah.
how real astrophysics works,
Yeah.
right?
Be more.
Yeah.
Yeah,
So I
well,
think, yeah. Anyway, it sounds like we're aware that it's all, thinking about it physically, it sounds like it's not going to be very easy to do this, but of course you have to do it because we have the detector, and if you
Those
make the
of you
detection,
who will be here during the weeks, I think Chuck Horowitz will be here in week 4.
right now.
And so we should remember to ask him these questions because he is the one who's thought the most about this and has done these simulations.
I have a question about more of the practical aspect of it. I took two things from this. One of them is it's very pessimistic, the prospect of detection of this, and the other one.
I should say that was my take. I mean, some people are not so pessimistic, but I think we've already heard why you might be pessimistic, yeah.
The other one is you have a couple of slides that is very expensive.
Yes.
They are not,
Yep.
Okay, given that there are other sources, could you tell us if there is a priority? And given that you don't have infinite computational resources in LIGO,
Yep.
is there a priority list of where they're going to invest the searches?
That's right. We don't invest very much in these searches ourselves because we use this Einstein at Home screensaver to get the so in other words, we devote most of our resources to doing N spirals. And then, so out of all the cores we have, a small fraction of them get devoted to doing these these smaller coherence times where it's not so computationally expensive. So we do some quick searches using a small fraction of our, really whatever's left over after N spiral is. Things are never running all the time, so you get some small fraction. But
By online,
let's see here, Einstein at Home.
online search for binary
Here we go.
neutron stars, not
Oh.
even binary particles.
Okay.
Binary neutron stars.
I thought there was more information on here than this, maybe. Okay. Most of,
Or is it burst?
It's CDC.
yeah,
Burst doesn't consume as much? No?
yeah, burst. So it's like 10, just to do our basic search, you might need 10,000 cores for CBC, and you might need 500 cores to do burst. And we also could use a few hundred cores over a course of months and do our quicker searches. But Einstein Home, this is the screensaver program, but here we got 100,000 computers, usually at any one time running. We've got like 100 teraflops of computing power around the world that's doing our deepest searches. So that's how we, and in fact, Einstein Home might do some CBC I think I'll tell you later, but if CBC wants to do a fully spinning processing search, you might need 100,000 cores to do that, and SF is asking us to really pin down that number much better than 100,000. Then we might end up doing that kind of search on this kind of computing.
Data is always going to be a problem. In
Yeah,
the
yeah.
case of Einstein at Home,
Yeah.
search for continuous waves, you don't ship a lot of data.
Yeah, we don't ship a lot of data. That's right.
So
But
small chunk. Whereas for any inspiral search, we need
Well.
to have a large amount of data.
well, I think though, but each job could be just working on one
If you use
half
like
hour.
AR filters, you could do that.
Yeah.
But we don't have the technology at the moment.
It's getting better
But
all
if
the
you-
time. The amount, Einstein at home amount of data is getting better all the time because of faster internet connections and bigger hard drives.
Not just that, I think people don't like their hard drives to be filled with some
Yeah.
data.
But
Not be sensitive to these things.
if 100,000 people are doing it, it turns out you can get a lot of computing power. Even that's a small fraction of all the people on the Earth, I guess. You can still win over what you. Well, maybe not over an Exceed type cluster if they could give us that dedicated time, but yeah. But they're not giving us. They're not giving it to us.
There are other reasons why you need dedicated clusters, because you need to produce triggers online for scientific reasons.
Yeah.
And these are reliable at some level, but it's not quick. I mean, the results come out typically, 1 year after the.
For our kind of searches, they definitely come out a year or so after, because
it's not online.
Yeah, the online search is 10,000 cores. The plan right now is to have about 10,000 cores at Caltech to send out results to telescopes from in-spiral type searches within minutes, or less. 10 seconds to minutes timescales. Yeah.
Have you asked NSF what is cheaper to use Exceed or Amazon Cloud?
Yes, we had to tell them that it's still too expensive to do Amazon Cloud. They can every once in a while have a great deal, like where it sounds like it looks like it's cheaper, but when you get into the details of what we actually need to do, they're not willing to give you sort of like, yes, for a year we'll let you have this price and use up our resources for that kind of thing. Yep. I mean, that's a rough answer, but so far every time we looked at it, it never works out.
All the 900 people can sign up for the trial period.
Yeah.
You're done.
It's part of your duties, like your sign-on shift and your trial membership.
Yeah.
Or let them advertise in the
Yeah,
papers.
but all those things, all of the stuff changes, so it could be the future. Things like that could be the future, but right now we're saying it's not. Exceed looks like where we're going to do our deepest searches for in-spirals and stuff would be happening on a cluster like Exceed, but that's what it seems like it's going to happen. Then we'll still have.
In the UK, we're putting in some money.
Yeah, we'll still have AEI. We'll still have Cardiff. Yeah. There'll still be clusters at Syracuse, UWM, ADI, and stuff too. But yeah. But the biggest resource is, right now, it sounds like Exceed is going to be the biggest resource that we get. But there's still some. It's not actually signed off anywhere near being signed off yet. So.
Any more questions? Well, let's thank Greg again. And just in case some of you may not come tomorrow, about the trip to Kamano Island, I can take 3 or 4 people, have other people decided on how we're going to get there, and